All right, hello everyone. I'm Kenrick Mock. I'm Dean of the College of Engineering here at UAA, and it is my pleasure to introduce our speaker today. Our speaker is Dr. Luigi Fortuna, who is a full professor of automatic control at the University of Catania in Italy since 1994. And his interests include robust control, nonlinear circuits and systems design, and has been Dean of Engineering faculty at his university up to 2012. He's also a IEEE Fellow since 2001, co-author of 12 USA patents, published 20 books with Springer, TRC Press, World Scientific, and others, and is editor-in-chief of the Nonlinear Engineering Journal. So we had the pleasure of Dr. Fortuna visiting campus this past summer, and he was gracious enough to give us a presentation for our seminar series, and we look forward to some future engagement with Dr. Fortuna and his university moving forward. So with that, I'll turn it over to you, Dr. Fortuna.
Okay. Good morning, Carrick. So it is a pleasure for me to give this seminar, and it is the summary of the research that we carried out with other people in Catania on the last 5 or 6 years, and is regards this imperfection, nonlinearities, and noise, essentially in dynamical systems. And the main topic of this discussion regards as these these facts that are considered negative in more cases in engineering are for us instruments to improve control system design. So this is the focus. Discover how imperfection could help engineers. Focus on how nonlinear dynamics could lead to some benefit. Discover the active role of noise. And the keywords are feedback systems, chaotic system, active use of the chaos. And we start with this very simple example. We have the ball that slide on the surface. The second ball is a ball that is running on the surface. This is the correct behavior of the ball. This is, as you can see, the first ball is ideal. The second ball is not ideal, is imperfect for the shape of the body. And the last one is too much imperfect. So the second one is the better for practical use of the task of the ball. And this is showed as imperfection could help the correct behavior in real case of the ball. As you can see, this is a second example. We have a road. In the figures that you can see, the roads does not work if the 3 points O, B, C are correctly on the line, and this could occur. Moreover, to avoid this fact that not permit the correct behavior of the road, some imperfection, some eccentric dynamic of the body is introduced. Now we go on some specific problems regarding the electronics. This has occurred in our lab. We used this integrated circuit in analog is an analog multipliers. So it's a circuits that make analog computation of a product of two quantities, x1 and x2. The perfect model said that the multiplication has been done exactly. But really, this does not occur because there are parasitic dynamics inside the device due to the technologies and the function that we have. So the behavior of the circuit does not include not only a multiplication but some other computation like this one and this one. Indeed it is hidden is in the behavior of the system and cannot be discovered. We used this multiplier to make some circuits, and we discovered that, for example, what we want to get, that was this oscillator, is not derived, but we derived a chaotic attractor as a chaotic circuit with an added values. So we can use at this point this parasitic effect to derive important nonlinear behavior of circuits with a chaotic behavior. And this is due to the imperfection of the circuit. Now it is another example that we discovered that we have. It is clear. This, as you can see, this is so it's a chaotic attractor, and we use this oscillator, this nonlinear typical oscillator, to drive piezoelectric robots. And we proved as moving the legs of this system, of these small robots, by using perfect, so it is not constant frequencies in the legs, and by using to drive the legs with chaotic circuits, the speed of the robots is increased respect the traditional one that is used when is driven by using a sinusoidal signal. This is another example as imperfections in signal allow us to improve the behavior. Another circuits, hence here an electronic circuits is a comparator, and as you can see, we have a circuit there where we have the configuration of the circuits. We have more resistor inside the circuits, but what we obtain is a chaotic strange attractor. It's, as you can see in the various in these figures. So it's by using these bifurcation parameters, we can have oscillation, chaotic attractors, double oscillations, and so on. But it is impossible to foresee this behavior in the circuit due to the fact that we do not have reactive components in this circuit external. So the parasitic components inside the circuits allow us to use this voltage comparator to derive chaotic oscillator. Now we have this study. We propose this electromechanical system. This electromechanical system is made by a number of coils that works like DC motors. But as you can see from this picture, the behavior of this coil is very imperfect. And if we will include more of this coil in this network, so more coils in this networks, what's happened is you have as we can see that when we are trying to start all the coils, not all the coils are working because the position of the coils are not exactly in the condition that allow to the coil to be powered. Therefore, our idea is to stimulate the system, this system. We have some vibration, and thanks to the imperfection of the coils, we try to stimulate the hidden behavior and to use noise, to use mechanical vibration to activate all the coil. After this has been obtained, we eliminate the stimulation, the mechanical stimulation, and the coils are all together working and running. So what is it is due to the self imperfection of each coils that itself stimulate the oscillation of the body of the systems, and they all together help each other to go on and to work and organize themselves in these experiments. This is very important because we, instead of controlling 10 coils, we controlled one vibration of the structure. This is the spike that show the dynamical behaviors of the current on each coil. So what is the model? The model is this. Generally, we have a system, it's a nonlinear systems where X are the state variables, while X tilde are the hidden variables. The hidden variables that are due to the imperfection. And we must stimulate these state variables in order to have a complete behavior of the system. So the second part of our task is to stimulate these subsystems and to favorite the interaction with the main body of the system. And in this way, we can control the system itself with the hidden state variables that are not remarked by the general model of the system, and that are essentially due to the imperfection of the system. Therefore, the main body of our control system is that we have here the system. Here we have here a loop, a controller, one controller that allow us to stimulate the body of the system and excitate and the stimulation of the hidden variables of the system. In that case, we stimulate the body, the mechanical body, with some switching condition, mechanical condition, and then is the system itself to organize itself. The equations are the classical reaction diffusion equation. So it is the reactive action, so the model of each coils in our case, and we have the coupling of by using diffusion coefficients of the various variables inside the system. Therefore, what is the guidelines of our study? To know in details the processing by performing a wide range of experimental observation in order to identify the hidden dynamics, to have a physical knowledge of the process, to get a reasonable mathematical model in agreement with the experimental measurements, using also identification techniques based on analysis, to distinguish between uncertainty of the system that is related to the parameters and added chimeral dynamics. Task to be obtained to get stable equilibrium points, to get suitable performance, to save the energy of the controlled system, to select the control system. In this case, what we represents the model of a single coils, and as you can see, these are two terms that allow us to define the model of the coupling of the various coils. And therefore, our task is to indicate as stimulating signals that allow us to discover hidden variables in the imperfect systems, and therefore to allow a self-organization of all the system. In practically, we use chaotic signals to stimulate the whole system. Then, therefore, we can see this is a first link between imperfection and nonlinear circuit, because we use nonlinear circuits like a noise, like a vibration, like a random vibration. But by using this type of signals, chaotic signals, we have some parameters inside the circuits to control it. And therefore, our actuators are stimulated by chaotic circuit. This is about how the equipments that we used in our study, and we have an electromechanical system with various structures, linear structure. We have circular structures, and we have actuators. We have to get a monitoring of the system, we have thermoelectric measurements and thermoelectric image that allow us to establish which is the circuits that absorb more energy respect the others. And of course, we have some circuits that allow us the digital controllers of the system. This is some results of a case study: steady state without control, experimental and model. So we have the coil this is the coils. This is the time where is measurements, and as you can see, the various difference of colors indicates as the various speed without control are working with different speed. If we'll use some regularization system, what we have? We have a startup condition when we put some signals and to give some vibration in order to stimulate all the coils. But when after some times, when the coils are all stimulated, we switch we switch the power, we decrease the powers, and we'll observe as a regularization is achieved. As you can see, after in this range of time, all the coils are working with approximately with the same speed. This is the same examples that I studied before, but it is reported in a circular framework. So it's a singular structure, and we have about 16 coils, but the principle is the same. And we have, you can see here, the actuator that allow us to stimulate the hidden variables that are stimulated by using, of course, chaotic circuits. And of course, we have here the characteristic of the angular speed of 16 coils. The first one, when we use a Chua circuit at 5 Hz, and the second at 16 Hz as a main frequency in the circuit. And of course, we can make an estimation of the time that allow us to have a regularization. Of course, if will requires short, as you can see, we have in these are the times, and smaller is the times. Smaller is the times indicates as a smaller is a good regularization of the circuit. And of course, what we want, what we wish, is to have a regularization of the speed, but with a limited consumption, electrical consumption. These are a summary of the same experiments that has been performed with various frequencies, with graph that allow us to have in the power, allow it to a regularization, and of course, if will increase the power, the regularization is achieved in small times. Though this is the compromise, to have a correct behavior and to have the small powers, but the consistent regularization of the speed. This is the wishing of the designer. Now, this art has been the task of this study has been devoted to have a platform for studying vibration, to use the chaos as active signals to allows the regularization, and to use for a large number of interconnected coils only few signals to establish a regularization of all the elements of the platform. And this is permitted, we can do is thanks to the imperfection of the system itself, to the nonlinearity and the use of chaos that essentially is like noise, is typical of nonlinear circuits. Now I jump immediately to a second item that is related to the nonlinearity and to the use of nonlinearity in a positive way, instead of avoiding nonlinearity. Generally, engineering try to linearize in electronics, in mechanics, and so on, to avoid drawbacks. This is a classical example, as for example, resonance does work in negative way, and in particular, this is the jumping resonance of the Tacoma Bridge that destroyed, that led to the destroy of the body of the bridge. Indeed, this is a nonlinear resonance. And I explain now what I mean for nonlinear resonance. So nonlinear resonance involves a non-symmetrical curve of resonance. And it leads to crash.
Back out of the danger zone, all stricken spectators are driven to safety.
So negative effect, dangerous, crash effects of nonlinear jumping resonance.
The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure?
Now, again, let us consider these experiments is in a small case, but in the principle is the same of jumping resonance, nonlinear resonance. We have a thin rods that is stimulated by sinusoidal mechanical vibration. And you can see the sound. Increasing frequency and now decreasing frequency. So what's happened is this thin shape. We have two resonance, one for increasing trends of the signal and the other one for decreasing trend of the frequency. Is like what's happened in the bridge. Anyway, it is a not desired behavior because we have two jumps in the frequency, in the resonance. Essentially, what's happened is again repeat now. So we have a sound at with frequency in increasing frequency and jumping, and when decreasing frequency, that are different. What's happened? Now here this is a shape of nonlinear jumping resonance. As you can see, we have a resonance when we gone up and the other frequency when we go down. So as you can see, we have the two up and down, and then down and up. So we have two lines where so inside the range of the resonance, we could have two behaviors, one that is up, another that is down. This is what's happening in nonlinear jumping resonance. That is terrible in the case of the bridge, of the crash of the bridge, and that is classically shown by using a rod vibration. But this is generated by a classical feedback of a linear system, of a classical second order linear system with a feedback with a nonlinearity, a cubic nonlinearity. This leads to this type of response of the system, auto response of the system. Our idea is to use this phenomena to measure the drift of a signal that is working. So, for example, the frequency of the power voltage signals that going from 60 hertz from in your country and oscillate in 58, 62. But we want to measure not only the frequency, but the drift of the frequency. This means how many times go down and how many times go up, and to have a trend in the time of this behavior. So we use this phenomena and to use this effect to design jumping resonance circuits in order to use them in for adopting sensors of drift frequency. This is a hybrid device made by analog components and digital components to make to realize this type of sensors. And we have it is interested the companies in this type of sensors. We have patents in this sensors, and this is essentially the shape of the signals, the output signals. The first one is a resonance up, and this is the stimulated signals. This is a sweep in frequency, and we have a resonance at this frequency. Moreover, if we come back with sweep in the in the opposite direction, we have a different frequency of shaping. This is a classical jumping resonance phenomena. This is what's happening. In this case, we can see that we have an input signal that is shaping. So the red indicates the up level, the up frequency response trends, while when we have green, we have the down. Measuring the interval when the green and the red is does occur is monitored by this display. So this number indicates the drift of the frequency, because it's going in the low and up graph of the jumping resonance. And this is a classical device that allows us to have a continuous monitoring of the drift frequency phenomenon. This is I intended as a dangerous nonlinearity can let us to derive opportunities to get new type of sensor, new type of device, useful and at low cost. Of course, the jumping resonance can be made in more pieces. So we have a nonic multi-jumping resonance and allow us to have a complete plots of the draft in various frequency ranges. And this is as you can see, is a research that is in progress in our labs, and it represents as our efforts in using nonlinearity as dangerous nonlinearities to get circuits with added values. Now, what is the last and immediate, and so it's as a very brief discussion. So the noise in nonlinear systems. So nonlinear systems, so if you have a noise in linear system, are very dangerous. While in nonlinear system is the level of noise is suitable, we could have what it is called stochastic resonance. This means that the hundred of signals of noise allow to transmit a signals in circuit with thresholds. So in thresholds are circuit with nonlinearity peculiarities. And thanks to this nonlinearity, if the added noise is suitable, we allow to transmit the sinusoidal signals in presence of noise. And this is what's happened. So without noise, we have no information. With noise, we have some information. This is stochastic resonance phenomena. So this means that we have a suitable level of noise level when the transmission of information achieves the maximum value. Now, if we view again our stochastic resonance, see our system with the coils that we showed before, we can review all we discussed in terms of imperfection, in terms of signal with added noise in the body. This allows us the vibration, the active vibration are the noise, and the noise help us to self-organization. So it is we can see the previous examples that I showed in terms of imperfection, now in terms of stochastic resonance effect. And in fact, we can stimulate the systems with various periodic vibrational control and will verify that the transmission or the effects of synchronization of the various coils is achieved when a level of noise is achieved. It's a suitable levels of noise. This gives us a measure of the time where the system is self-organizing. Therefore, this example shows us as the previous study can be reformulated in terms of added values and in terms of stochastic resonance effect. In conclusion, a class of controller system with hidden dynamics and added broad spectrum noise of chaotic system has been proposed. The behavior of two experimental spatial extended systems has been illustrated. The proposed control strategy is effective also in terms of power consumption, stimulated hidden feedback system capabilities to reduce artificial feedback loop. So this is the main task. If we stimulate internal state variables, we could avoid to add more and more feedbacks. And of course, apart the second topic that regards sensors, we want to get focus as vibration and noise could help us, but is another values in real life. A very important item is in the evolutionary scale and the noise in the brain. And we now show, okay, the conclusion as essentially due to the fact that imperfections, noise, nonlinearities are each linked together. Without nonlinearities, imperfections are dangerous. Without imperfections, we cannot have some benefits. And without the noise and without nonlinearities, we cannot control more and more complex systems in a simple way. This is the sentence. There is an intrinsic universal effect in distributed system among imperfection, nonlinearity, and noise. Now it is a brief flash. When we was in Anchorage, we discovered this leaf and the phenomena of a parasitic of this leaf. It is a labyrinth. Its labyrinth is for us a classical example that we have in information science. And the labyrinth identification has been done by Professor Chua by using nonlinear cellular networks. Nonlinear cellular networks are the links or more nonlinear, very simple systems that works together to have a highly parallel massive computer systems. So we were stimulated by the observation that we make in Anchorage, myself and Professor Buscarino, to try to have a classification of this leaf by using cellular nonlinear networks that essentially are based on the concept that previously I discussed in this talk. These are the reference on this topic, and now I thank you for attention and thank you for giving me this opportunity.
All right, thank you, Dr. Fortuna. So for anyone that's working on completing the online survey with a professional development credit, there's a password, and the password for this one is Imperfections. All right, so I can open it up to any questions, either in the room or online. Yeah, I think we're online, Andy.
No questions online at the moment.
All right. Anything here in the room? So I thought that was a nice tie-in with the leaf miner that you found. So I have one question. I think it's pretty fascinating about the benefits of noise in the system, and you touched on that a little bit at the end about the brain, but I'm wondering if you are looking at this in other systems outside electromechanical, or for example, neural networks, or any of these other systems where you could discuss the benefits of adding noise.
Because
The Tacoma Bridge pictures were very intriguing, and one forgets how much the change was going on at that time. I really like the analogy that he put together on that.
Yes, yes. So the bridge is classically the answer to the crash of the bridge has been given to classical resonance. Moreover, recently, after the knowledge of jumping resonance, the effect has been addressed to the nonlinear resonance, so it's not symmetric curves of resonance, because the bridge has been stimulated by frequency variable signals in increasing and decreasing. Therefore, we have two jumps, one for upper frequency and the other for lower frequency. And this is not regular jumps, allowed a crash because stimulated more parts of the bridge that had solicited by different frequencies, and therefore leads to a big crash of the bridge.
Thank you. That was very interesting.
And that you have a patent on the drip sensors that you discussed. Is that something that's been further developed?
Yes, yes. So the sensors we conceived is sensors that allow us to measure not only the frequency but the drift of frequency in one direction and the other direction, and to have a monitoring how time is down the nominal frequency and how time is up the nominal frequencies. So it is a sensor that you could put in your plug.
All right.
Thank you.
All right, yay. Thank you very much.
Thank you very much.
Thank you very much.
All right.
So we